doing some basic percentages things. Nice easy percentages work. We're going to move on from there today. 2B, we're looking at real numbers and approximations. Real numbers are made up of many special types of numbers, and they are denoted using the symbol R, capital R, that you see there. We had a few other symbols that we introduced last lesson. This is the one for real numbers, capital R. Okay, so you can see your real numbers here at the top of the table. Real numbers can be divided into rational and irrational numbers. So our irrational numbers are most of our surds. And I say most because technically I could say square root of 9, which looks like a surd, but because it equals a whole number, it would not be irrational, okay? So any of our surds that can't be simplified to whole numbers are irrational. Also things like pi and e, something that you're going to learn about in advanced maths, are also irrational numbers. Our rational numbers are the whole numbers, they're fractions, they are decimals as long as they are terminating decimals or recurring decimals that we can turn into fractions, okay? Our rational numbers can be divided up even more into the fractions and the integers. Integers being your whole numbers, positive, negative, or 0, and fractions, obviously you know what fractions are. Okay, so that's how we name all of our different types of numbers. Now, going through a few things here that I know you've seen many times before. Rounding. When rounding to a certain number of decimal places, count only those places after the decimal point. So if I say I want 2 decimal places, I count 1, 2 decimal places, and I round off after that. You guys know how to round, okay? Been doing that for years. Scientific notation. When rounding a certain number to a number of significant figures, begin counting from the first non-zero digit. I'm not sure why that's in there. That's kind of in the significant figures part. But scientific notation, which is also called standard form, is when we want to write a very large or a very small number. Okay, we don't want to have to write 9 with 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Too many zeros, okay? We want to be able to write it much shorter to save ourselves some time. So we have scientific notation. And to do scientific notation for a very large number, we always put the decimal point straight after the first non-zero number. And then we times by 10, and the power of the 10 is how many places that you move that decimal point. Ringing bells? Yeah, cool. All right. Significant figures. The concept of significant figures is related to rounding, but it is not exactly the same as decimal place rounding. When you are using very large or very small numbers, the smaller digits are not significant. For example, a crowd of 79,894 people, we say is about 80,000. So we have that has been rounded to one significant figure. The 8 at the beginning there is the one significant figure, and everything after that has been rounded down to zeros. If you are asked to do the rounding, to round to a certain number of significant figures, we always count the very first non-zero digit. So that's down here. We count the first non-zero digit, which is starting on the very left-hand side of the number. All digits that are not zeros, so everything other than 0 is always significant. Always, always, always. Okay, it's only the zeros that have a little bit of a special case. The zeros are not significant except when they are between non-zero numbers or at the end of a decimal number. Okay, it's going to be easier to see that though, isn't it, than me just saying that. So for example, 207, the zero is in between. Is that significant? Is that a significant zero? Yes. If I put the 0 at the end, is that 0 significant? No, correct. If I put the 0 in front, is that significant? In front of a decimal like that, is that significant? Who agrees? It's actually a no. Okay, it is only significant when it's between, the other one was, or at the end of a decimal number, which is like this, a 27.0. When it's at the end of a decimal, after a decimal point, it is always going to be significant. So this case and this case is when the zeros are significant. The other times it is not significant. Okay? Intervals. This is something a little bit new. At least the naming part is a little bit new in here. An interval is a connected part of a number line. Okay, so remember when you draw those little number lines, you put the dots at the end and you connect up. It's that little, that's what we call that. We call that an interval. Okay? A closed interval, you're going to have to identify what a closed interval is something like this. -2 less than or equal to x less than or equal to 3. Meaning that it contains its endpoints. If you think of the diagram, this is a really rough one because I don't have a lot of room here. So if -2 was here and +3 was here, I should have all my numbers in between. It's when you have closed in circles at those endpoints. Okay? So when you have those equal to signs on there, the closed in circles, that's making it a closed interval. Makes sense. Closed in circles, closed interval. So that then hopefully follows that an open interval is going to be the ones that do not have any of the equal signs on those inequalities. So the less than signs are in there, okay, because they're the open circles, open interval. Yeah? Great. An interval like this one, -2 is less than x, which is less than or equal to 3. One of them is a less than, one of them has the equal to sign. We can't classify that as being either open or closed because one's open and one's closed, so we say it's neither. Yeah? It has to be both of them closed or both of them open for them to be classified as opened or closed. A bounded interval has two endpoints which are bound to the interval. So these ones that we've been talking about, because they're 2 points and we're bounding our bit in between, they're all examples of bounded intervals. Those three, all those three that I've just been talking about are all bounded intervals. However, an unbounded interval is when I only give you one value to work with. So I say x is less than or equal to 3. It's unbounded because that less than 3 can keep going all the way down to negative infinity. It's just going to keep going forever. It's unbounded. Or if it was a greater than, it would keep going to positive infinity, way up as big as you want it to be, unbounded. Okay, so you need to be aware of what those words mean, okay? A degenerate interval, sounds a bit derogatory there, is a name that we give to a closed single point. So it doesn't have an inequality sign on it at all. It would be something like x equals 3. It's just a one single point, a degenerate interval, one closed single point. Okay? All right. So a few quick questions to practice. Classify each of these as being open, closed, or neither. So you're looking at the inequality signs. So I have a less than and I have a less than or equal to. So who wants hands up? Who wants to tell me what that is? Open, closed, or neither? Tia? Neither. Neither, thank you, yes. B, we're looking at the signs. Less than or equal to. Max? Closed. Because both of them have equal to signs on them. X is greater than 3. It is open. There's no equal to sign on there. It's also unbounded, but we weren't asked that. Okay, we were asked open, closed, or neither. It's open. And D, there's no equal signs on there, so that one's going to be open. Great. Okay, question 2. Practicing rounding to significant figures. Okay, let's find something we always need a little refresher on this, okay? I know it seems like an easy question, but we can do with a refresher from time to time. So we start from the very left-hand side, and I like to put a little dot above the ones I want to keep. So I need 3. I want the 4, I want the 2, and I want the 3. They're the 3 significant figures. They're not zeros. They're my 3 significant figures. Everything after that is going to have to round off to zeros. My next number is a 4. 4's round down, so I just change it into a 0. My final answer is going to be 4, 2, 3. There's my 3 significant figures. The 4 rounds down to a 0, and I still also have those other 3 zeros. You can't just leave the zeros off, okay? They still have to keep, the numbers still have to keep their place values, okay? It still needs to be 4 millions, in the place values. You can't delete the zeros, even though they're not significant, all right? Let's try part B. Start counting from the left. The 0 out the front, it's not significant. Okay, it's before the decimal place, not significant. The 1 is the first one, then the 2, and the 5. There's my 1, 2, 3 significant figures. The 8 onwards, I need to round off. Because it's an 8, I will round up. So I keep the 0, because I have to keep my place values. I need the 1, the 2, and the 5 will round up to be a 6. Once I chop the rest of those decimal places off, don't replace them with zeros when it's after the decimal point. What happens if I do that?
Nothing.
Well, it doesn't change the size of the number, but zeros after the decimal point are significant. So if I put zeros on there, I'm actually giving myself, like if I put some zeros in here for the ones I chopped off, I've now given myself 6 significant figures because those 3 zeros on the end are significant. Okay, so we have to leave them off to have done that correctly. Part C. Start counting from the left-hand side. The 2 I want, the 3 I want, and the 0, it's between other numbers, it is significant. Okay? So the next number is a 4, so it's going to round down. So I keep the 2, decimal point, keep the 3, keep the 0. I do need to keep that 0 because that's my third significant figure. Okay, 1, 2, 3, done. And for D, all those zeros out the front are not significant because they're in front of the decimal number, okay? So the 2, the 9, and the 5 are my significant figures. The 4, my dots aren't very clear there, let me make those bigger. The 4 needs to round off, it will round down, and we won't change it to a 0, we'll just chop it off, okay? So we go, how many zeros there? 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6, 2, 9, and a 5. All right? Is that okay? Wonderful. Question 3. Calculate these to 4 significant figures. It just means that when you're rounding stuff to significant figures, you're going to be doing like an area question or a volume question, and you just have to remember to round it at the end. So you're going to be doing the calculation on your calculator, so get your calculator out, and you're just typing these ones in. So 2.3 plus 8.5, exactly as it is, 3.1 equals. Okay, so often it's handy to write that whole number down first and then do your rounding part. So I'll do that. It was 1.060108, and there was a few more numbers after that, but that's plenty. Okay, so start counting our significant figures. I want the 1, I want the 0, I want the 6. Everything else rounds off. The next number is a 0, so it's after the decimal place, chop it off. Okay, so it's a 4. Oh, I want 4 figures. Oh, I need to count it. Thank you. That one, I changed it to 4 significant figures. I'm still doing 3. Thank you. I do need that 0. Chop the 1 off. That is the attitude, you two. 1.060. Okay. And again for B, just type it in, get the decimal first, and we want 4 significant figures. So, fraction, cubed root, you can use shift there, cubed root of 34, and minus 2.4 on the bottom. All right? So I get negative 1.349838. Okay, so 4 significant figures. I want the 1, I want the 3, I want the 4, and I want that 9. Okay, this hasn't happened yet. The number after that 9 is an 8, which means I need to round up a 9. Okay, which will round, so I round the 9 up, which is going to have to round the 4 up to become a 5. It bumps it up the line. Minus 1.3, the 4 has been bumped up to a 5, and I need that 0 on the end to have 4 significant figures. All right, hopefully that one's pretty straightforward in 2B there. We're also going to start on our surds today.
2C.
Yeah, 2C. So 2C. No, we have swimming carnival tomorrow. That's why we're doing 2. All right. So surds. Year 10. I'll call you 10. Sorry, I'm old habits. Haven't graduated you guys to year 11 yet. All right, year 11. Come on. Stop talking, please. Okay. So we talked about rational numbers. A rational number can be written as a ratio or a fraction. We usually do fractions. Okay. An irrational number, which is what we're looking at now, cannot be written as a ratio or a fraction. And we typically call them a surd. A surd is a special type. There is a few others, as I mentioned before, the pi and the e. There's a few other special numbers that are also irrational, but most of the irrational numbers that we work with are surds. Now, to simplify surds, you must always use your perfect square numbers. And as a reminder, it says here, those magic numbers, to remind you, are 4, 9, 16, 25, 36, 49. So it's 2 times 2 is 4. 3 times 3 is 9. They're all your squared numbers. 4 times 4 is 16. Monty? Okay. Typically, up to about 100 is the ones that you're frequently going to use. Very rarely we'll be using these really massive ones up here. So it's usually less than 100, okay? So a reminder, because I know you've done this many times before, to simplify a surd, we need to find one of those perfect square numbers that we can divide our 45 by. Hands up, what perfect square can I divide 45 by? Yes, 9. So 45 is 9, don't write this down yet, 9 times 5. Now, I said don't write this down yet because what I would like you to do, instead of writing that step down, is to straight away split those into 2 surds, just to save yourself some time. Okay, so we've identified the 2 numbers, but we split it to be square root of 9 times square root of 5. It doesn't matter which one you put first, but I like to put the perfect square number first, because that then makes it really easy to simplify, because the square root of 9 becomes a 3, and the square root of 5, which doesn't simplify anymore, just sits there on the end. Okay, and that's simplifying. Done. Part B. If there is a number out the front, just leave it there for a minute, and we simplify the surd part like we just did. So 40. Hands up. What perfect square can I divide 40 by? Monty? 4 is my perfect square, and I do 4, yes, times 10. So I split that surd to be square root of 4 times square root of 10. Now, the square root of 4 is 2. Now, I'm happy for you to do this in one step, but I'm going to do it in 2 just to make sure that everybody can follow what I'm doing. The square root of 4 is 2, and I still have the square root of 10 there. You could have straight away multiplied that 2 with the 5 to get 10 square root of 10. So I'm happy for you just to show that line there and that line there. But I just want to make sure that you are clear on how to get there, what you are doing to get that final answer. Question 2. Write these problems here as a single surd. meaning that I want everything to be under one square root sign. I don't want the number out the front. So it does look like a single surd already, I know. But it means that whole number out the front, I want to get it underneath that square root sign as well. It's kind of the reverse of what I was just doing. So what I do is the 6, I want to square that. 6 squared is 36. 6 is the same as square root of 36. Okay? And I have that times by the square root of 2. And like I said, I'm reversing what I was doing before because I can push those two surds together to make 1 just times the numbers underneath. 36 times 2 is 72. Okay, let's do it again. The 5 out the front, we want to put it back under a square root sign. So 5 squared is 25. 5 is the same as root 25. I also have the square root of 3 there. Now I combine the two surds, multiply what's underneath. 25 times 3 is 75. All right, one more question typed down here, number 3. We get to the simplifying part. Think of surds to be a lot like algebra. You can add and subtract surds if they are like surds, just like the like terms of algebra. You can add x's with x's, but not x's and y's, right? So it's the same thing here. If they have the same square root, I can add or subtract the coefficients out the front. So the first one, they are all root 5s. So all I need to do is go 3 plus 6 minus the 1. There'd be a 1 there. So that is 8 root 5s. Okay? Just as if they were x's. Just adding those numbers out the front, and the root 5 stays the same. In part B, none of those surds are currently the same, but we should always be looking to see if we can simplify, and maybe they will become the same. Okay? So the first term I have there, the 5 root 3. 3, that's not going to divide by one of my perfect square numbers. That cannot be simplified. So 5 root 3. The second one, the 2 root 27. Okay, leave the 2 out the front, but the 27, what perfect square number? 9 times 3, yes. So square root of 9 times square root of 3. Minus sign. Okay, I'm doing each one step at a time, then I'll come back and do the next line. So 8. What can I divide by? 4. Five root 3 stays the same. In the second term, I can square root the 9. I'm going to do this in one step this time. So square root of 9 is 3 times the 3 with the 2 to get a 6 root 3. And the last term, square root the 4 to be 2 root 2. Okay, now they're not all like surds, but the first two are. They are root 3s. So 5 plus 6 makes 11 root 3. The 2 root 2 is different, so it sits at the end. All right, easy peasy. That's it.